Thank you, Malheiro, again. And to continue, I would like to invite Marquez to talk about extension of the Nambu-Jona-Lasinio model to hadronic matter containing strangeness.
Can you listen me?
Yes.
Okay. Well, good morning. My name is Marquez, and I present next part of the work I'm developing as a PhD student together with the Nuclear and Hadron Physics Research Group at Universidade Federal de Santa Catarina, under the supervision of Professor Débora Pérez Menezes. The complete understanding of the quantum chromodynamics phase diagram represents a challenge in both theoretical and experimental physics, as we see the QCD phase diagram in high energy physics talks. The best known region of the diagram, beyond of course the low temperature and low density region where we live in, is the high T and low chemical potential sector, close to the vertical axis. These regions are probed by very high energy collisions at HIC and LHC, and also are the only region where we can obtain solutions directly from QCD through lattice-QCD methods. The region of high densities, low temperatures, where compact stars are, for example, and where we suppose an first order phase transition might occur, are not treatable by these approaches. In this scenario, effective methods remain a good source of information about this region inaccessible otherwise. QCD shows the spontaneously breaking, partial breaking, of chiral symmetry by the non-vanishing quark condensates that occur due to the non-perturbative nature of QCD breaking. This mechanism provides an explanation of the huge difference between bound state observed masses and the sum of the masses of the forming particles. For example, the valence quark bar masses in a proton contribute to only 9.4 MeV of the total 900 MeV mass of the nucleon. Quark masses can be understood as being dynamically generated by the spontaneous chiral symmetry breaking in this context. The first theoretical approach to the chiral symmetry breaking in a relativistic quantum field theory was performed by Nambu and Jona-Lasinio in 1961, anteceding the proposal of quarks and the QCD formulation. The NJL model aimed to describe increasing interacting nucleons, motivated by the fact that this interaction holds a partial conserved axial vector current associated to the approximate chiral symmetry. Since it imposes the nucleon mass to be small or even zero in the Lagrangian level, the spontaneous symmetry breaking, in analogy to the BCS theory of superconductors, provides a mechanism which generates dynamically the large nucleon mass. Here in the equation 2, we have the gap mass with the behavior shown in the figures below. Here I show the NJL model Lagrangian for considering matter with 2 or 3 quark flavors with an additional vector interaction channel. And this channel makes the equations of state stiffer. if we want to. So even though the original NJL model was proposed considering nucleonic degrees of freedom, the lack of confinement becomes a problem within the QCD framework because it also doesn't bind the quarks together, which made it to be reinterpreted as a schematic pre-quark model. So we use it to describe the quark-gluon plasma. The parameters GS, the scalar channel coupling, lambda, the cutoff we need to employ to regularize the theory, and in the case of SU3 NJL, the parameter K, which is a mixing flavor term, are fitted to reproduce experimental parameters of pion decay, for example. GV is a kind of tree parameter of the model. The grand canonical thermodynamic potential is obtained, and here we have the gap equations for the mass and for the effective chemical potential when we are considering non-zero densities. So the fact that NJL Lagrangian does not confine the Fermion fields, as I said, also implies that it is unable to describe the saturation properties of the nuclear matter, because if you use the nucleonic degrees of freedom, we want them to bind in nucleus. However, it can be fixed by the inclusion of an extra channel representing the scalar vector interaction, this term. The same logic can be applied to many other channels of interaction, aiming to improve the description of other important nuclear bulk properties, which give the origin to the so-called extended NJL model family. One version of this NJL model developed by our group is shown here. We call them PPM. This model allows to the description of nucleonic matter, protons and neutrons. And the parameter sets shown are fitted to fulfill nuclear experimental constraints, the saturation point, incompressibility, symmetry energy, its slope, but also to reach the 2 solar masses threshold when applied to describe compact stars. So these are approved by both nuclear and astrophysical constraints. It's a good equation of state. Here I show an example of the equation of state for the SU2 quark matter and nucleonic matter described by the models I talked previously. When describing hadronic matter at very high densities, for example, compact stars, the appearance of hyperons is expected. The hyperon formation process could take place significant role in hyperonic density environments, as I said, in compact stars or in heavy ion collisions. Yet, if you want to look at stable deconfined quark matter that should have a strangeness content to fulfill the Bodmer-Witten hypothesis, it's important to have strangeness also in the hadron phase, because hadron-quark deconfinement process probably conserves quark flavor fractions. So we must have strangeness also in the hyperons, in the nucleonic matter. No, sorry, in the hadronic matter. So this novel Lagrangian we developed here is built considering protons, neutrons, and lambda-baryons. Each interaction channel shows an SU3 symmetry. So here we have a chiral model for 3 kinds of particles. And lots of terms to fit the nuclear saturation properties. Here I show the equations of state derived from the model, and here the gap equations. Another feature that follows from the S3 Gell-Mann matrix formed by their phase is that the whole term, the G whole term, is the isobacter channel, doesn't cancel out for symmetric matter. It happens to the S2 version of the ppm. In equation 10, you can see this rho 8 isn't zero, even when rho proton equals rho neutron and rho lambda 0. The rho 3 cancels out. It comes from the Gell-Mann matrix, the 8th Gell-Mann matrix. So in an exploratory search of parameters for this model, we found these sets and many others that fulfill some nuclear matter quantities constants. This model is way harder to parameterize than the S2 version because the fact of G-hole don't cancel out and its crossed channels also won't vanish, influence even the symmetric matter quantities, the saturation density point. So we have way more.
Excuse me, Marquez.
Okay.
5 minutes to finish.
Okay, I'm already there. So these parameter sets fit the saturation density point, the saturation density binding energy, and the symmetry energy at the saturation point, but doesn't fulfill the incompressibility model, incompressibility modulus, for example, which is way important to describe compact stars, for example, to have an EOS stiff enough. Here I show examples of the equation of states for this PPMM NJL. The solid line for symmetric proton-neutron only nuclear matter, and the dashed line for equal fractions of protons, neutrons, and lambdas. It's a work in progress, as I said, and better fits we will obtain soon. So this equation of state is way more stiffer than it should. But anyway, we can see the softening effect of the hyperinclusion. Now we talk a bit about a first study where some of the NJL model versions present are used to investigate hadron phase transition, hadron-quark phase transition at zero temperature. This theoretical framework allows us to explore the QCD phase diagram within a true model formalism, but where chiral symmetry is present in both hadronic and quark phase equations of state. The quark coexistence point is determined by the Gibbs conditions as shown in the figures. For the equations of state, in the left, the transition is thermodynamically forbidden because the lines doesn't cross. The right panel shows how this point is a lot model dependent. Sorry, I missed the slide. Just a second. Here. Oops. Then I missed the slide. Sorry. Here I have the values for the points for symmetric matter, taking SGL2 versus SPPM hadronic model. So the values for ME and P. And here for same thing, but for stellar matter, which includes leptons and post-charge neutrality and chemical equilibrium conditions. In having strange quarks modeled by the SU3 NJL model and proton and neutron matter modeled by the PPM. So it's a preliminary study, but later we want to have SU3 matter values. That's it. Thank for the organizers and you all for listening.
Okay, thank you. Thank you, Marquez. Question, Malheiro?
I can see the chat.
Unmute. Okay. My question is very interesting work, but you know that exist some problems here that we should at least try to let's put to analyze. Okay. The thing is that now, if you are nucleons and not quarks, okay, and you have chiral symmetry as you have, okay, you have your couplings. Now, of course, you have a nucleon and antinucleon condensate in the vacuum. That is, I don't know how much is the value to produce your mass in the vacuum, okay, of the nucleons. So now the nucleons will not have zero the free mass in the vacuum. Okay, first thing. Okay, and second thing is that you now are going to have a nucleon and antinucleon bound state. Okay. With a mass, okay, you need to solve Bethe-Salpeter equation with that nucleons to see the mass of this state, of this, let's put the pion made by nucleons, because now pion is made by quark and anti-quark. Now you have a pion, or I don't know, it's not a pion, let's put a pseudoscalar isovector excitation that it comes from the mass of this nucleon and antinucleon condensate. How much is this number? And exists any particle that can be related to that possibility in the spectrum of pseudoscalar particles and isovector ones? You understand what I ask, or is too complicated?
I'm not sure about what you're asking, but the nucleon masses aren't zero in the vacuum state. They are the nucleon masses, 939 MeV. I'm not sure about what you're asking.
So you are saying that you don't have any breaking of chiral symmetry spontaneously, is what you are saying in your model.
Vacuum, the chiral symmetry is broken when we
is not broken spontaneously in this model. So it's what you are saying. Yeah.
Yeah, the chiral symmetry is restored as the density increases or the energy increase.
Okay, and so in that, so my point is that what is did you check if you don't have any bound state with this n bar coupled states?
Well, I don't know. I don't check.
Because if you know, or because in this case, my point is how the pion comes here, okay? Or not the pion, let's put how this excitation of neutron and antineutron comes. So
can I talk?
Yes.
Actually, what you are doing is that you were considering this idea that was developed with this the Nambu-Jona-Lasinio exactly because it had no bound states. So this works very well if you have quarks. you probably know that, but the NJL model was first developed to describe nucleons, but then it was abandoned because it didn't, it could not have bound states. So for quark states, you have some kind of, how can I say, interpretation for the condensates, but this is not exactly the same interpretation you have if you were going to have if you include nucleons instead of quarks. So we did not analyze this, whatever you were calling pionic analog states.
Yes,
we can look at
that
that.
was why they are abandoned.
Yeah, we can look at that. But you see, we do have restoration and breaking of chiral symmetry exactly as when we have quarks. And even when we have quarks, you don't need to have a real restoration of the chiral symmetry, because you can use this bare quark mass different from zero. You can have this as a 5 MeV, for instance, or 3 MeV. So the picture is exactly the same. The difference is now that we have this mass related for the breaking and restoration of chiral symmetry for nucleons. And what this has already been published a while ago, but what Kawa is considering now is the inclusion of hyperons, lambdas only. So we can do this.
Okay, but in that sense, let me tell you, in fact, this, not because I want to take credit, okay, but this is what you are doing is not Nambu model, okay, sorry if you don't allow me. You are doing contact interactions, okay, with nucleons, okay? And so this is what, in fact, many times ago we showed that Valeshka model could be done as for, because the Nambu model means that you have a gap equation for the vacuum. You don't have here, so it's not Nambu.
I don't think it's true. No, if you look at the original Nambu-Jona-Lasinio model, the original, the very first one, it was exactly like that for nucleons.
Yes, but if not, okay, you can talk about Nambu. It's not Nambu. It's a point coupling model only, because Nambu means that you need to have a gap equation in the vacuum not different from zero. You don't have, as you said. So you don't have any vacuum. So it's really is a point coupling model, okay, with nucleons like Odilon did and the first itself and the
but then we can talk about it.
Or am I wrong? I don't know.
I think you were wrong.
Yeah.
But we can talk about that later.
Yeah, because you restore a chiral symmetry because you are only calculating finite density. You only have nucleons, okay? You never have any vacuum that has any there. So
but we can calculate.
Of course, you have type of Lagrangian of Nambu, but you can see as a point coupling Lagrangian with all the possible terms you can include that conserve your symmetry, so on. But I don't know. Okay. But now I understood. So you don't have any. So if I don't know. So you need to see what you have now when you have this is what I'm saying is that when you decrease the mass of your nucleon, okay, that you are getting, what you have nucleon and condensate different from in your finite density state. Okay, that's correct.
Excuse me.
That's correct or no?
Let me.
Okay.
We have another question.
Continue. Yeah.
Sorry.
Okay. But think about what happens with that particle when you are changing density. What is the mass of that nucleon and nucleon condensate? Okay, that relate to the analogous pions. What happens with that particle? Okay. But that's fine. Thank you.
Veronica, could you ask your question?
I just had a quick question about the plot that show the option of having the same amount of protons, neutrons, and lambdas.
Okay.
Was called symmetric or
This
something
one.
like that. Equal amount, that one. So what are the conditions exactly that you impose to get the same amount of the three of them?
The same chemical. Let me remember. It was a little bit ago when I did
What's the
very,
difference between the two lines, condition-wise?
yeah. This one we have the same density of lambda protons and neutrons. The same baryonic density. And this one we have protons and neutrons density equal half of the total baryonic density and lambda density 0. Right?
Okay. No.
It's zero
No.
temperature, everything I showed here.
I think that's what she wants to know is, Veronica, if you look at the upper curve, there are no lambda
Yeah.
particles,
Just
just
protons
protons and neutrons. That's usual symmetric nuclear matter. And if you look at the curve below, then lambda particles are included. Maybe the same chemical potential is a little bit artificial, but we are just trying to see what comes out from the model.
Yeah.
Okay.
Right?
Okay. Thank you, Karl and Marx.
Thank you.
And no more question, no more comment. And this session is finished. Thank you.
Thank you.